Ever feel like your online life is this giant, super complicated video game, but the rule book for keeping your stuff safe keeps getting updated with patches and new challenges all the
No,
time?
absolutely. It changes constantly.
Well, today we're basically grabbing that strategy guide.
Yeah.
You've shared some really amazing info about how different digital fortresses are built, from your own phone all the way up to these massive cloud networks.
That's the plan.
So our mission,
Yeah.
to kind of decode those blueprints so you, our listener, feel like you've got the inside scoop on how it all actually works.
Exactly. We're taking a deep dive into the security behind different tech setups, everything from those trusty servers maybe humming away in a back room somewhere,
Right.
to the really sleek, ever-evolving world of cloud computing. The materials you tool together are fantastic. They cover everything from locking down your personal devices to the really intricate security measures protecting huge online infrastructures.
And this isn't just for the tech gurus out there listening, right? Understanding these concepts gives you a real advantage. You'll get a clearer picture of how your data is protected, or maybe where there might be room for improvement.
Yeah, definitely.
Whether you're thinking about your company's security or trying to understand why data breaches keep popping up in the news, or even just choosing the best cloud storage for your photos, this stuff matters.
It really does.
We're aiming for those aha moments today, not, a snooze fest through a technical manual.
For sure. Our approach today is to break down the big picture, kind of step by step. We'll explore that fundamental difference between keeping everything in one place versus having it spread out.
Okay.
Then we'll navigate the different flavors of cloud computing, public, private, and a couple of others you might find intriguing. We'll even touch on some of the newer approaches like serverless and microservices. And of course, we'll explore the classic network security tools that form the foundation of it all. Think of us as your guides through this, let's be honest, sometimes confusing landscape.
Okay, sounds good. Let's jump into this whole idea of centralized versus decentralized security first.
Yeah.
You give some really helpful analogies in the materials. One was McDonald's, which you described as centralized. So what does the security playbook look like in that kind of setup?
Okay, yeah. Think of McDonald's where, most of the big decisions and the overall policies come straight from corporate headquarters.
Right, top down.
Exactly. That's like a centralized security model. They set the rules for pretty much everything, including how data is handled and protected across all their franchises, right? This top-down approach, it can lead to very consistent security practices. Everyone's operating under the same guidelines.
Makes sense. One central team calling all the security shots. Then you contrasted that with Toyota and blockchain as examples of decentralized systems. How does security work when the power and responsibility are more spread out?
Well, with Toyota, while there's obviously a main headquarters, their regional divisions have quite a bit of autonomy to make decisions based on their local markets. And similarly, blockchain technology distributes records across loads of different computers. So in a decentralized security model, the authority and responsibility for security aren't all concentrated in one spot. Different departments or units might have more flexibility, maybe a greater say in their own security measures.
So if security policies are set at the top in a centralized system, it sounds like things would be pretty consistent, across the board.
Exactly. Centralized models typically have really strong top-down policy enforcement. The aim is for a uniform security stance throughout the entire organization. Everyone follows the same standards, which can make it easier to manage and keep tabs on things.
But in a decentralized setup, you mentioned there could be more flexibility. Is that always a good thing, or could it lead to a bit of a security free-for-all sometimes?
That flexibility, yeah, it can be a bit of a double-edged sword. On one hand, different parts of a decentralized organization can tailor their security to their specific needs and the unique risks they face. That's good.
Right.
But on the other hand, it can definitely introduce inconsistencies. You might end up with some units having state-of-the-art security and others that are, less protected. And that could potentially create weak links in the overall chain,
Yeah, I can see that. So what happens when a security alarm goes off? How might a centralized company react compared to a decentralized one?
So in a centralized model, you'd likely see a more rapid, coordinated response. The central security team can quickly issue alerts, deploy necessary fixes, and manage the response across the entire organization relatively efficiently.
Like a security SWAT team deploying from headquarters to handle the situation everywhere at once.
Precisely. But in a decentralized environment, the response to a threat might be more fragmented. Local units might have the authority to handle incidents themselves, which could be good if they have specific local knowledge, right?
Yeah.
But it also carries the risk of, well, a lack of coordination, maybe slower overall response times, and potentially inconsistent handling of the security incident across the different parts of the organization.
Okay, that gives us a pretty good handle on centralized versus decentralized. Now, let's talk about something that's become such a huge part of our digital lives: cloud computing. You mentioned that the shift to remote work and greater mobility has really accelerated its adoption. Why is that exactly?
Well, cloud computing offers the kind of flexibility and scalability that are just essential for remote and mobile workforces today. People can access their data and applications from, well, virtually anywhere with an internet connection.
Right.
And companies can easily adjust their computing resources up or down as needed. It just ensures everything stays accessible and operational. It doesn't really matter where people are working from.
All right, it's like having your office accessible on pretty much any device anywhere you are. But you also outlined 4 main types of cloud models. Let's start with the most common one, the public cloud. What does that look like from a security perspective for someone like me who uses it probably without even thinking about it?
Okay, the core concept to grasp with the public cloud is multi-tenancy. This means that the cloud service provider, think of the big ones like Microsoft Azure or Amazon Web Services, they host multiple different organizations. Potentially even your company and one of your competitors on the same underlying physical hardware.
Wait, hold on. So my data could be sharing a server with someone else's data. That sounds a little unsettling.
Yeah, that's a natural reaction. And the inherent risk in these multi-tenant environments is that the actions of one tenant could theoretically impact another. I mean, if one organization has a security breach, there's a potential. Although, cloud providers have put in significant security measures to prevent this.
Okay.
But there's still a potential that it could somehow affect other tenants on the same infrastructure. The source material even highlights the potential for data breaches within this model. So while the providers have strong safeguards, your responsibility lies in making sure your own configurations and access controls are absolutely rock solid to prevent lateral movement or data exposure.
Okay, public cloud sounds a bit like sharing an apartment building. You kind of hope everyone else is careful with their locks. So what's the alternative? You mentioned a private cloud.
Right. A private cloud is essentially the opposite of multi-tenant. With this model, a company either owns and manages its own dedicated hardware and infrastructure, or it has a cloud provider hosted on servers that are exclusively for their use. It's single tenant.
Ah, okay.
This gives the company much greater control over their data, and it's generally considered more secure because, well, they aren't sharing resources with any other organization. The example given of the U.S. military using a private cloud really emphasizes the level of security it can offer. It's kind of like having your own private island for your data.
A private island for data. I like that. What about this community cloud you mentioned? That's a new term for me.
Yeah, it's less common, but interesting. Think of a community cloud as maybe a shared island, but with a specific group of trusted neighbors.
Okay.
In this model, organizations with shared interests, maybe they're in the same industry, might pool their resources and collectively pay a cloud provider to build and host a customized application on dedicated infrastructure. They share the costs, but they have their own separate and secure instances of the application. It can be a cost-effective solution when, off-the-shelf software doesn't quite meet the specific needs of that community.
Interesting, like a co-op for cloud resources within a specific field. And the last one is a hybrid cloud. That sounds pretty self-explanatory, like a mix of the others.
Exactly. A hybrid cloud is just a combination of using both on-premises infrastructure, your own servers in your own building, and public cloud resources. The example given was a manufacturing company with a physical factory, but using the public cloud to support its mobile international sales force. Their office is basically a car and a phone connected to the cloud.
So they get to pick and choose what goes where. What are the security challenges of managing a setup like that? It sounds, more complicated to keep secure.
It definitely adds a layer of complexity, yeah. Managing security across both your own infrastructure and the public cloud demands really careful coordination. You need to make sure consistent security policies and practices are applied across both environments, and there can be unique challenges related to data integration and network connectivity between the two. It's not always simple.
Okay, so we've got the different types of cloud deployments covered. Now, you also talked about cloud services like things that maybe used to run on our own computers now being offered as a service. Can you break down a few of those and what the security implications are for us? You mentioned IaaS, SaaS, and PaaS.
Absolutely. Let's start with IaaS, or infrastructure as a service. Picture this as the cloud provider giving you the foundational building blocks of a data center, the servers, storage, networks, basically the bare metal. It's kind of like getting an empty building, but the plumbing and electricity are already installed.
Okay, so they provide the basic structure. What am I then responsible for setting up and securing?
You're responsible for pretty much everything else. You have to install the operating system, configure the network devices, and, crucially, keep everything patched and updated with the latest security fixes. The cloud provider takes care of the physical security of their data centers and the availability of the underlying infrastructure, but securing what you actually put on that infrastructure, that's your job.
Got it. They hand me the shell, and I build and secure the inside. What about SaaS? Software as a service. It's probably what most people think of when they think of using cloud applications, right?
Exactly. SaaS is when the cloud provider hosts a complete software application that you access over the internet, usually just through a web browser. Think of everyday tools like email services, CRM systems like Salesforce, or even office productivity suites like Microsoft 365.
So I just log in and start using it.
Mm.
What are my security worries in that scenario? It feels like they handle most of it.
They do handle a lot. With SaaS, the cloud provider shoulders most of the security burden for the application itself. They manage the underlying infrastructure, the software updates, the overall security of the platform. However, you are still responsible for your data that you put into the application and how you manage who can access it. So, for example, creating strong, unique passwords and definitely using multi-factor authentication for your accounts within that SaaS application, that remains your responsibility. Also, you typically can't modify the application itself.
Okay, so they secure the app, I secure my access to it, my data within it. Makes sense. What's PaaS, platform as a service? That sounds a bit more geared towards techies or developers.
It is, yeah, definitely more focused on developers. PaaS provides a complete environment for building, deploying, and managing applications. The cloud provider gives you the underlying infrastructure, servers, storage, networking, plus things like development tools, middleware, operating systems, and databases. Think of services like AWS Elastic Beanstalk or Google App Engine.
So developers can just focus on writing code without worrying about setting up all the underlying systems. Sounds nice.
Precisely. The cloud provider handles a significant chunk of the infrastructure management, but the security of the platform itself is often a shared responsibility. The provider secures the underlying infrastructure and the platform services, but you, as the developer, you're responsible for the security of your application code and how you configure the platform services you're actually using.
You also threw in SECI as SaaS. Those sound like something out of a techie dictionary.
Yeah. SaaS is security as a service. This is basically where you outsource specific security functions to a specialized managed security provider. Things like identity and access management, continuous threat monitoring, or even managed firewall services can fall under this category.
Okay.
And SaaS, or anything as a service, is really just an umbrella term for the ever-increasing variety of other cloud-based services becoming available, like network as a service or desktop as a service. The crucial takeaway with all these as a service models is you really need to have a clear understanding of exactly who is responsible for which aspects of security.
And you had that responsibility matrix in the materials, didn't you? It clearly showed who handles things like physical security versus who's in charge of patching it. Really highlighted that division of labor is key.
Exactly right. That matrix is absolutely key to understanding that moving to the cloud doesn't mean you're just handing over all security responsibilities. Nope. It's really a partnership with the cloud provider, and knowing exactly where your responsibilities start and end is fundamental for maintaining a robust security posture.
Okay, that clears up the cloud world quite a bit. Now let's get down to the nuts and bolts. Securing the actual network, the servers, and the devices we use every day, what you call the hosts. You mentioned a multi-layered approach to network security. What are the essential layers in that security sandwich?
Right. Think of network security like building a castle with multiple rings of defense.
Right.
At the outermost ring, you've got your firewalls. These act as the gatekeepers, right? They scrutinize all incoming and outgoing network traffic and block anything that doesn't have explicit permission.
Okay.
They operate using access control lists, or ACLs, where the default stance is basically deny all, nothing gets through unless specifically permitted. This drastically reduces the potential attack surface.
So only the traffic I've pre-approved gets past the guards at the gate. Got it. What's the next layer of protection? You mentioned IDS and IPS.
Okay, moving inward, you have intrusion detection systems, IDS, and intrusion prevention systems, IPS.
Yeah.
While firewalls control traffic based on predefined rules like source and destination addresses or ports, IDS and IPS are more about actively looking for and responding to suspicious behavior in real time. An IDS will identify potential threats and send you an alert. Think of it like a security camera spotting someone acting suspiciously.
Oh.
An IPS can go a step further and automatically take action to block or prevent those threats from entering your network, like the security guard actually stepping in to stop that suspicious person. They work hand in hand with the firewall to create a more robust security perimeter.
And so IDS is kind of like a silent alarm, and
Mhm.
IPS is more like an active security intervention.
Yeah.
What about SIEM? That sounded like it provides a much broader view of what's happening across the whole network.
Exactly. Security information and event management, or SIEM systems, are like the central intelligence hub of your security operations. They collect and analyze logs and data from all sorts of different network devices and security tools, firewalls, servers, applications, you name it.
Yeah.
The SIEM system can then correlate seemingly unrelated events to identify potential security incidents that might otherwise go totally unnoticed. For example, if the system sees, say, unusual login attempts from overseas, followed by a large file download from an internal server, the correlation engine can flag that as a potential breach, even if each individual event on its own looked kind of normal. This gives organizations a much more holistic understanding of their security posture and enables more proactive defense.
So it's not just looking at individual warning lights flashing, but seeing the whole dashboard and how everything connects together. Smart. You also emphasize the importance of securing specific types of servers. Why are domain controllers and SQL servers such high-value targets for attackers?
Well, domain controllers are the central authority for managing user accounts and authentication on a network. They basically verify who you are when you log in. So if a domain controller gets compromised, really bad news. Attackers could potentially gain access to a huge number of user accounts, essentially getting the keys to the kingdom. And SQL servers, they often store the really sensitive data, customer information, financial records. The source specifically mentioned credit card info is a critical example. Securing them is absolutely paramount to prevent devastating data breaches.
Makes perfect sense. And you also mentioned mail servers and video conferencing apps as being increasingly targeted these days. Why are those suddenly on the attacker's radar so much?
Well, mail servers have always been a frequent entry point for attacks because they handle communication with the outside world, right? That makes them prime targets for phishing campaigns and malware distribution.
True.
And video conferencing applications, especially with their massive surge in popularity for both personal and business communication recently, well, they've also become really attractive targets for cyber criminals looking to eavesdrop on sensitive conversations or maybe gain unauthorized access to meetings. More usage means more attention from the bad guys.
Yeah, that figures. And with more and more of our files living in the cloud, how do we ensure those are protected? You mentioned cloud storage solutions having their own security.
Yeah, cloud storage providers like Amazon S3 or Azure Blob Storage, they offer a whole suite of built-in security features. These typically include encryption to scramble your data, both when it's being transmitted to and from the cloud and also when it's just sitting there at rest on their servers.
Okay.
They also provide pretty robust access controls, allowing you to precisely manage who can view and modify your files, along with monitoring tools to detect any unusual or suspicious activity related to your storage.
So the cloud providers build security into their storage systems.
Good. What about our own laptops and phones, the devices we actually use every day, the hosts? They often feel like maybe the weakest link in the security chain sometimes.
They absolutely can be. End user devices are frequently the first line of defense or maybe the first point of attack.
Yep.
And if they get compromised, attackers can gain a foothold into the broader network. That's where endpoint security solutions come into play.
Think of antivirus software to detect and remove malicious programs. Then there are more advanced endpoint detection and response EDR tools for continuous threat monitoring and analysis, and mobile device management MDM systems to secure and manage mobile devices that access company resources. And as the source material rightly emphasizes, multi-factor authentication, or MFA, plays such a crucial role. It adds that extra layer of security, requiring you to provide multiple forms of verification before granting access to an account. It's really essential now.
MFA, yeah, it can be a bit of a hassle sometimes when you're in a hurry, but definitely worth it for the added security. Okay, let's explore some of these newer architectural approaches you mentioned. First up was infrastructure as code. That sounds like something only developers would really care about.
Well, while it's heavily used by developers and IT operations teams, yeah, the underlying concept has much broader implications. Infrastructure as code, or IAC, is the practice of managing and provisioning your IT infrastructure, things like servers, networks, databases, using machine-readable code or scripts, often written in languages like YAML or JSON.
Okay.
Instead of manually clicking through configuration menus on different devices, you define your entire infrastructure in code.
So it's like writing a detailed recipe for your entire tech setup and then automatically having it built exactly to spec. What's the security upside to doing things this way?
IAC offers several really key security benefits. It introduces automation and consistency, which significantly reduces the risk of human configuration errors, and those errors can often lead to security vulnerabilities.
Yeah, makes sense.
Because your infrastructure is defined in code, you can use version control systems, just like you do with application code. This means you can track every single change made to your infrastructure, easily roll back to previous secure configurations if something goes wrong, and even conduct code reviews to identify potential security issues before they're ever deployed. The source mentioned major cloud providers like AWS, Azure, Google Cloud, and popular tools like Terraform and Ansible that heavily support IAC. The key insight here is that your security focus kind of shifts from manual configuration hardening to secure coding practices for your infrastructure definitions themselves.
That makes a lot of sense. If you automate securely, you get secure automation. But if your code has flaws. Okay. Next up was serverless computing. The name kind of implies there are no actual servers involved. It sounds a bit like, I don't know, magic. What's the reality there?
Yeah, that's a common initial thought. There are definitely still servers involved, lots of them. They just aren't servers that you have to manage directly.
Oh.
The beauty of serverless computing is that the cloud provider takes over all the operational overhead of managing the underlying servers. As a developer, you focus solely on writing and deploying your application code. The cloud provider handles the provisioning, the scaling, the patching, the physical security of the infrastructure, all that stuff.
So they take away all the server management headaches for me. That sounds great. What's the security angle for someone using an application built on serverless architecture?
The significant security benefit here is that you're effectively offloading a considerable portion of the infrastructure security responsibility to the cloud provider, who typically has vast expertise and massive resources dedicated just to security. As the source points out, the customer doesn't own or directly manage the physical servers. Their applications and data are hosted and secured by the provider. This can often lead to more secure solutions than maybe smaller companies trying to manage all their own server infrastructure could achieve. However, and this is important, it's crucial to remember that you, as the customer, are still responsible for the security of your application code and the data you process and store within that serverless environment. And as a bonus, it can be very cost-effective because you generally only pay for the compute time you actually use, not for idle server capacity.
Okay, less server wrangling for me, which is good, but I still need to make sure my application code itself is secure. Got it. Finally, in this section was microservices. The diagram you included looked like taking one big application and kind of chopping it up into a bunch of smaller, independent pieces. What's the thinking behind that, and how does it impact security?
Right. Microservices architecture involves breaking down a large monolithic application into a collection of smaller independent services that communicate with each other, usually through well-defined interfaces called APIs. Each microservice focuses on a specific business function. Think of a large e-commerce website, for instance. Instead of one giant complex application doing everything, you might have separate microservices for managing user accounts, the product catalog, the shopping cart, payment processing, and so on.
So instead of one massive program, it's like a team of smaller, specialized programs all working together. How does that distributed approach help with security, though?
Well, one key security advantage is improved fault isolation. If one microservice experiences a problem or even a security breach, it's isolated. It's much less likely to bring down the entire application. They're designed to be resilient and handle failures more gracefully. Also, because they are smaller and independent, it can actually be easier to secure individual microservices. You can apply specific security measures tailored to the unique needs and risks of just that one service. The source also highlights other benefits like increased agility, independent scaling of individual components, faster development cycles, easier maintenance, and the fact that careful design of these microservices can definitely enhance overall network stability too.
Interesting. So if one part of the application gets attacked, the blast radius is potentially much smaller. Okay. Now let's really dive into the nitty-gritty of network infrastructure. You had a table with all sorts of devices like WAMPs, routers, and switches. Let's start with something relatively straightforward. What exactly is a wireless access point?
A wireless access point, or WP, yeah, that's the device that allows your Wi-Fi-enabled devices, your laptops, smartphones, tablets, to connect to a wired network without needing a physical cable. It essentially acts as a bridge between the wireless world and the wired portion of your local network.
Okay, that's pretty clear. What about a router? That's usually the main box I have at home that gives me internet access, right? Or is that the modem? Or both?
Often it's combined with a modem in home setups, yeah? But the router part performs a couple of crucial functions. First, it connects different networks together, for example, your home network to your internet service provider's network, which in turn connects you to the vast internet. That's why it's often called the default gateway for your local network. Second, it uses something called a routing table to figure out the most efficient path to send network packets, those small chunks of data that travel across the internet to their intended destination. The analogy in the source material of a router being like a post office for IP packets is actually quite good. Think of IP addresses as street addresses, and the router figures out the best delivery route for each letter or packet.
Okay, so it's the traffic director for my network, sending things out to the wider world. What about a switch then? Sometimes they look physically similar to routers. How are they different?
A switch is primarily used within a local area network, or LAN, to connect multiple devices, computers, printers, servers that are all on the same local network. It maintains a special table called a Content Addressable Memory, or CAM table. This table stores the unique hardware, addresses the MA addresses of all the devices connected to its ports. So when a data packet arrives at the switch destined for a device on the local network, the switch looks at the destination and NV address in the packet header, checks its CAM table, and forwards the packet only out the specific port where that destination device is connected. It's much more efficient than the old hubs, which just broadcast everything everywhere.
Ah, okay. So a router directs traffic between different networks, like my home and the internet, and a switch directs traffic between devices within the same local network.
Got it. You also mentioned VLANs in the context of switches. What exactly are those? Sounds virtual.
They are. VLANs, or virtual local area networks, are a way to logically segment a physical network within a switch using software. Instead of having to physically separate devices onto different switches if you want to isolate them, you can create virtual isolated networks right there on the same physical switch. This lets you group devices together based on department, function, or security level, even if they're plugged into different physical ports on the same switch hardware.
How does that work? The source gave a great example. An IT department and a finance department could be on separate VLANs but using the same physical switch. Their network traffic is kept isolated as if they were on completely different physical networks. This logical separation is often achieved through tagging the network traffic, adding a little label so the switches know which virtual network each packet belongs to.
That's clever, like creating virtual walls and separate hallways within the same office building using software.
Yeah.
You also briefly mentioned ARP. What role does that play in all this networking communication?
Right, Address Resolution Protocol, or ARP. It basically acts as a translator between IP addresses, those logical addresses used for routing across networks, and ME addresses the physical hardware addresses burned into network interfaces. When a device on your local network wants to talk to another device on the same local network, it usually knows the destination IP address, but it needs to know the physical MAC address to actually send the data frame at the lower network level. ARP is the protocol that figures out this mapping. It essentially shouts out to the local network, hey, who has this IP address? Tell me your MC address.
Okay.
And just a reminder from the source material, for the CompTIA exam specifically, when they just say switch, they generally mean a layer 2 device. That means it operates at the data link layer of the network model and deals primarily with empty addresses. It's also worth noting, ARP can be vulnerable to spoofing attacks, where a bad actor tries to associate their MC address with someone else's IP address to potentially intercept traffic.
Got ARP is the address lookup for local network communication, and switches are generally layer 2 for exam purposes dealing with MPs. You also listed a few other important devices, load balancers, WAFs, and NIP. What do those bring to the network security party?
Okay, a load balancer does pretty much exactly what its name implies. It distributes incoming network traffic evenly across multiple servers hosting the same application or service. This helps prevent any single server from getting overwhelmed, ensuring better performance and, importantly, higher availability for your applications.
Makes sense, like a traffic cop spreading cars across multiple lanes.
Exactly. Then a web application firewall, or VAE, is a specialized type of firewall. It's designed specifically to protect web servers and their applications from common attacks that target known web vulnerabilities, things like SQL injection or cross-site scripting, XSS. It understands web traffic specifically.
Okay, so it's like a bodyguard specifically for web applications and in the IPS.
And Network Intrusion Prevention System, or NIPS, as we touched on earlier with IDS, actively monitors network traffic in real time, looking for malicious activity based on signatures or anomalous behavior. But unlike just detecting IDS, it can automatically take action to block or prevent those attacks from succeeding right there on the network.
So load balancers keep things running smoothly under heavy traffic. WAFs are bodyguards for web apps. And 9PS actively try to stop bad guys in their tracks on the network. Now, you talked about physically isolating networks creating air-gap systems. That sounds incredibly secure, maybe the most secure, but also pretty inconvenient for day-to-day use, right?
It is the most extreme level of isolation you can possibly achieve, and yes, as you said, it often comes with significant inconvenience. An air-gapped network means that the devices within that network have absolutely no physical or wireless connections to any outside network. None. Not the internet, not even other internal networks within the same organization.
Wow. So how do you get data in or out?
The only way is by using removable media, like USB drives, and those are usually very carefully controlled and scanned. The example of an R&D department using an air-gapped computer to safeguard highly sensitive trade secrets really highlights the kinds of scenarios where this level of security might be absolutely necessary. It virtually eliminates the risk of remote cyber attacks.
So it's like a digital vault with absolutely no doors or windows connecting it to the outside world.
Okay.
What about logical segmentation then? We've already talked about VLANs, but you also mentioned subnetting as another way.
Right. Logical segmentation is the practice of dividing a network into smaller, more manageable, and more secure segments using logical boundaries created in software rather than needing physical separation. Subnetting is a key technique for achieving this at the IP layer.
How does it work?
It's the process of breaking down a larger network IP address range into smaller, distinct subnetworks, or subnets. This helps to reduce the broadcast domain, that's the area of the network where all devices see broadcast messages, which can improve network performance. But more importantly for security, it helps contain security incidents. The analogy used was containing a fast-spreading computer virus within a smaller, isolated subnet to prevent it from easily infecting the entire network. It limits the blast radius.
Okay, so subnetting helps to quarantine potential problems by shrinking the network neighborhood. And VLANs create those separate virtual networks within a switch at layer 2. You also introduced software-defined networking, or SDN. That sounds like a really cutting-edge approach to managing networks.
It is a more modern and flexible approach, yeah. In traditional networking, the management functions like configuration, the control functions, figuring out routes, and the actual data forwarding functions are all tightly coupled together within each individual switch or router.
Okay.
SDN separates these different planes. The control plane, which makes the intelligent decisions about how traffic should be routed and what security policies should be enforced, is centralized in an SDN controller. Think of it as a central brain for the network. The data plane, which consists of the actual switches and routers doing the forwarding, simply follows the instructions it receives from this central controller.
So instead of each individual network device figuring out its own path, there's a central coordinator calling all the shots for routing and policy. How does this separation help with security specifically?
Well, this separation allows for much more dynamic and efficient management of network resources overall. But from a security perspective, SDN enables really granular control over network traffic and the ability to implement security policies in a much more agile and responsive way. For example, if a threat is detected in one part of the network, the SDN controller can potentially reconfigure network paths almost instantly and isolate the affected segment in near real time, helping to prevent the attack from spreading.
That sounds incredibly powerful, like being able to instantly reroute traffic around a security incident or quarantine a problem area automatically.
Yeah.
Now, even with all this talk about cloud and advanced networking, we can't completely forget about the more traditional on-premises setup, right? Are there still valid reasons why a company might choose to keep their infrastructure in their own physical building?
Oh, absolutely. As the source material points out, for organizations in highly regulated industries with very strict compliance requirements, think healthcare with EPA, or finance with PCI DSS, maintaining sensitive data on their own premises can provide a greater sense of control and help them meet those specific regulatory obligations more easily.
Okay, compliance is a big one.
Definitely. Also, some applications that require extremely low latency access to data, maybe high performance computing or real-time analytics, might still benefit from on-premises solutions just due to the physics of data travel, the physical proximity of the resources.
Nice.
And finally, let's be realistic. Many companies have invested heavily over years in older legacy systems that are deeply integrated into their core operations. The cost and complexity of trying to migrate these sometimes ancient systems to the cloud can be really prohibitive. So on-prem isn't going away entirely anytime soon.
So sometimes the familiar in-house approach still makes the most sense for various reasons. Now let's circle back to some of those specialized systems and architectures you brought up. You mentioned containerization. In simple terms, what exactly is a container in the software world? Sounds like shipping.
That's actually a great analogy. Think of a software container like a lightweight, self-contained package for an application. It bundles together everything that application needs to run correctly, the application code itself, all the necessary software libraries, supporting dependencies, configuration files, all into a single portable unit. This means the application can run consistently across lots of different computing environments, whether it's a developer's laptop, a testing server, or a production environment in the cloud, pretty much regardless of the underlying operating system differences. The source even had a diagram illustrating how containers are isolated from each other but can share the host operating system and necessary libraries, which makes them very efficient compared to full virtual machines. It is kind of like shipping an application with all its required parts already packed in a standardized container, so it can be easily deployed anywhere that supports that container format, like Docker or Kubernetes.
So it's like shrink wrapping an application with everything it needs so it can travel and run reliably anywhere. Cool. You also touch on virtualization, again, specifically focusing on VDI. How does virtual desktop infrastructure relate to security?
Right, virtual desktop infrastructure, or VDI. This is a technology where a cloud provider, or maybe an organization's own data center, hosts virtual desktop environments like a Windows or Linux desktop for users to access remotely. Often, they use what are called thin client devices, which have minimal local processing power and storage.
Oh, yeah.
These virtual desktops are typically pooled together and based on a standardized operating system image, which gives the IT department a lot of central control. From a security perspective, this can be a big win because the actual computing and data storage happen in the secure, centralized data center environment, not on the user's potentially less secure endpoint device.
I see the benefit there.
Yeah. If a virtual machine happens to become compromised, it can often be easily wiped and reset to a clean, known good image. Furthermore, sensitive data remains secure within the data center. Even if a user's thin client device itself is lost or stolen, there's usually nothing critical stored locally on it. The source also briefly mentioned application virtualization, like Microsoft AppV, which isolates individual applications from the underlying OS. This can help with compatibility issues, but also enhance security by preventing applications from messing with each other, or the OS.
So VDI keeps the actual data and processing locked down in a secure central location, making the endpoint devices themselves less of a security risk. Okay, now let's tackle IoT, the Internet of Things. We have smart devices literally everywhere these days, from thermostats to doorbells to refrigerators. What are the main security challenges that come with all these interconnected gadgets? It feels kind of messy.
Oh, messy is a good word for it sometimes. The sheer volume and the increasing variety of IoT devices create an absolutely massive and often poorly defended attack surface. One of the biggest challenges is simply the lack of standardization in security practices across all the different manufacturers. This leads to a really wide range of security vulnerabilities out there.
Yeah, you hear about that?
Data privacy is also a huge concern, as these devices frequently collect vast amounts of personal information, which needs to be properly protected. Insecure communication is another major risk. Many IoT devices transmit data over unencrypted channels, making them vulnerable to eavesdropping. The often very long life cycles of many IoT devices, combined with a lack of consistent security updates from manufacturers, leaves them exposed to known vulnerabilities for potentially years. Physical security is also a factor. Physical access to an IoT device can sometimes allow attackers to tamper with it or extract data. Supply chain risks, where malicious components could maybe be introduced during the manufacturing process, are also a growing concern. And finally, frankly, many users just lack awareness of basic security practices for their IoT devices, making them easy targets. The source really underscores that the sheer number of connected devices dramatically expands the potential points of attack. It's almost like the Wild West out there still, isn't it? I remember reading about baby monitors being hacked. That's a stark reminder of the vulnerabilities in these everyday connected devices we trust.
Yeah, that's creepy. It definitely sounds like securing the IoT landscape is a huge and multifaceted problem with no easy answers yet. What about ICS and SCADA systems? Those sound like something out of a high-tech industrial thriller movie.
They are very real and incredibly critical systems. Industrial control systems, or ICS, and supervisory control and data acquisition, or SCADA, systems are used to monitor and control essential industrial processes, things like power generation and distribution, water treatment plants, manufacturing facilities, oil and gas pipelines, even building automation systems like HVAC. They are absolutely fundamental to the operation of much of our critical infrastructure.
So if those systems were to be compromised, the consequences could be, well, pretty severe, right?
Absolutely catastrophic, potentially. Because they control such vital services, they are highly attractive targets for sophisticated cyber attacks, including from nation-states. The source material points out that SCADA systems often run on similar software, sometimes even standard operating systems like Windows, as regular computer systems. This makes them susceptible to many of the same threats and vulnerabilities. The example of the Stuxnet virus attack on Iran's uranium enrichment facility, which physically damaged centrifuges, that tragically highlights the very real-world dangers and the potentially devastating consequences of successful attacks on these types of industrial systems. The stakes are incredibly high.
That's a truly sobering thought. Okay, you also mentioned RTOS and embedded systems. Where do they fit into this complex security picture?
Right. Real-time operating systems, or RTOS, are specialized operating systems designed specifically for applications where precise timing is absolutely crucial. Think things like flight control systems in aircraft, advanced navigation systems, or maybe industrial robotics. Security is obviously paramount for these because any compromise or disruption could have immediate and potentially devastating physical consequences.
Yeah, definitely don't want the flight control system hacked.
Exactly. And embedded systems are essentially specialized computer systems that are integrated within larger products. Think of all the electronic control units, ECUs, in a modern car. They manage everything from the engine and transmission to the anti-lock braking system, ABS, airbags, infotainment, the list goes on. Or consider the smart components in your home: thermostats, smart locks, security cameras, even appliances now. Securing these embedded systems is becoming increasingly critical as they become more interconnected and complex. The development of autonomous vehicles, for example, makes the robust security of their embedded control systems literally a matter of life and death.
So from our household gadgets all the way up to critical infrastructure and even the cars we drive, there's just this vast array of specialized systems that require really strong, often unique security measures. Okay, finally, let's talk about keeping everything running smoothly and reliably, this concept of high availability.
Yeah.
What does that mean in the world of technology?
High availability, often abbreviated as HA, refers to a system's ability to remain operational and accessible to users, even in the face of hardware failures, software glitches, power outages, or other unexpected disruptions. Cloud providers, for instance, often tout their high levels of uptime, sometimes referred to as 5 nines, that's 99.999% uptime, which translates to just over 5 minutes of potential downtime per year.
Wow, that's impressive. How do they achieve that?
They achieve this really impressive level of availability primarily through redundancy. That means having multiple copies of data and critical system components, often located in different physical locations or even different geographical regions.
You gave the example of Geozone Redundant Storage, or GZRS, in Azure with data centers in, say, England and Scotland. How does having data in multiple places like that contribute to high availability?
Exactly. With something like Geozone Redundant Storage, your data isn't just duplicated within a single data center building. It's replicated across multiple separate facilities called availability zones within the same primary geographic region, like England. And then it's also replicated asynchronously to a completely separate secondary geographic region, like Scotland.
Okay, multiple copies everywhere.
Right. So in that England and Scotland example, if an entire data center in, say, London were to experience a catastrophic failure, fire, flood, whatever your data, would still be readily available from another data center within England, a different availability zone, and also eventually from the replicated data centers up in Scotland. This geographical distribution ensures that your data remains accessible even in the event of a major outage affecting an entire building or even a whole region. It's like having a backup of your most important files, not just on a different drive in your house, but also stored safely in a completely different city or even country.
That sounds like a pretty solid safety net for important data.
Mhm.
You also listed a number of key considerations for designing secure infrastructure towards the end, things like availability, resilience, cost, responsiveness, scalability. Can you quickly touch on why each of those is so important when people are actually building these systems?
Absolutely, they all tie together. Availability, as we just discussed, is paramount for ensuring continuous access to data and services for users keeping the lights on. Resilience is closely related. It refers to the speed and effectiveness with which a system can recover from failures and get back online. Think load balancers helping here, or automated recovery in the cloud.
Oh, yeah.
Cost is always a huge factor, right? And it's crucial to consider not just the initial purchase price, but the total cost of ownership over time. Maintenance, support contracts, service level agreements, SLAs, and comparing that to the pay-as-you-go model often associated with cloud services.
Right, TCO.
Responsiveness ensures that users have timely interactions with systems and applications. No one likes lag. Scalability is the ability of the infrastructure to efficiently handle increasing demands for resources, maybe growing user numbers or seasonal peaks, like that toy manufacturer example needing more capacity at Christmas.
Mm-hmm.
Ease of deployment affects how quickly new systems and services can be rolled out. Automation tools like IAC, VDI, containerization really help here. Risk transference involves using contracts like SLAs to shift some of the financial risk associated with outages or performance issues to third-party providers, like guaranteeing database recovery time.
Okay.
Ease of recovery is critical for business continuity. If a major incident does happen, how quickly can you get back? Patch availability ensures that systems can be kept up to date with the latest security fixes, although the source noted there can be situations where patching customer-managed stuff isn't immediately possible or allowed. Ensuring sufficient and reliable power is absolutely fundamental, UPS generators. And finally, the availability of compute resources, especially the cloud's ability to provide on-demand capacity almost instantly, is essential for many modern applications, particularly things like serverless. All of these considerations need to be carefully balanced when designing a secure and reliable infrastructure that meets an organization's specific needs and, realistically, its budget.
Wow, that really was a deep dive. So as you, our listener, can probably see now, the world of security architecture is incredibly diverse. There are all these different models, and each offers its own unique sets of strengths and, well, challenges too, whether it's the centralized control of a traditional on-premises network, the incredible flexibility of the cloud, but with that shared responsibility model we talked about, or maybe the ultimate isolation of an air-gapped system. The choices that are made have really profound implications for keeping our digital world safe and secure.
And what's particularly fascinating to me is the way these different approaches often intersect and just continue to evolve. We see it with hybrid cloud deployments becoming so common and the ever-increasing, almost overwhelming need to secure all those interconnected IoT devices we discussed. This is a landscape that is constantly changing, and having a solid understanding of these fundamental architectural concepts provides you with a really crucial framework for navigating it effectively, whether you're in IT or just trying to understand the world around you.
Absolutely. So considering all these different ways of building and securing our technology infrastructure, here's something to think about. What do you think will be the biggest security challenge for organizations, maybe even for us as individuals, in the next 5 years, especially as we continue to rely more and more on these incredibly complex and interconnected models we've explored today? It's definitely something to keep pondering.